Hello, good morning everyone. Am I audible?
Yes, sir.
Yeah, okay. So let's start. Today we'll look at Huffman coding, primarily to represent data. Anytime we look at our file or anything, mostly what we use is what is called ASCII encoding, and that means each character gets fixed number of 7 bits or 8 bits. There's a huge amount of data, and we know that not all characters appears the same frequency. Can we change our encoding scheme to make it better that uses less space? And that is what the Huffman encoding is all about. As an example, consider that we have a text file which consists of, let's say, a program or anything, and it uses ASCII encoding, and each character is 7 bits. For example, letter A is 0x41, letter B is 0x42, and they use 7 bits. For example, A is 100. Sorry, there is an error in letter A. 1 minute. Yeah, this should be the case. Yes. If you look at letter A, it is 7 bits, 4, 1. Letter B is 4, 2, and each letter uses 7 bits. And that means if my file has total 1000 characters, I would end up using 7000 bits of storage. If you imagine we have a larger file data, and we know that in any text, all 26 alphabets does not come in the same frequency. Can we use that information that some letters appear more often than the others? And for those letters which appear more often, we can use a shorter encoding size compared to those letters which appear much less, and we can give them longer encoding size, and that would give us a overall saving of encoding scheme. And that primarily what the Huffman, the code is, or Huffman, and we look at how do we build up about it. That's what we look at. And essentially, so let's look at example there. For example, consider, let's say we have, once you go to 5th sem or 6th sem or 7th sem, you need to choose electives. And let's say there are 5 electives available to you: 561 Java programming, 562 artificial intelligence, embedded systems, .NET framework, and cloud computing. And past experience shows that we know that 50% people, let's say, take cloud computing, 25% people use Java programming, AI is taken by 12.5%, embedded systems and .NET, very low number of people. If I need to choose all the, let's say, elective choice for all the students, let's say assuming I have 100 students. Now, since I have these 5 subjects, I need to encode this 5. So that means I at least need 3 bits for encoding these 5 subjects. So one could be, I can say 000 for Java programming, 001 for AI, 010 for embedded systems, 011 for .NET, and 100 for cloud computing. And other 3 spaces, which is 101, 101, 110, and 111, not used. That were the case. Now, given this, and I'm not to record choices of, let's say, 100 students. So for student number 1, we'll put encoding, student number 2 encoding, student number 3 respective encoding. And so if I have 100 students total, I would need 100 into 3, because each subject is encoded using 3 bits. and I end up getting using 300 bits. We know that the cloud computing is taken by 50% people. So can we give a shorter code to this and longer code to, let's say, embedded systems are taken less? That probably give us better scheme. So in this case, let's look at for 100 students when each takes 3 bits, and let's say our encoding for the, as an example, for the first 5 students would be just a 0, 0, 1. First student, second student takes encoding 0, 0, 0. Third student 0, 0, 0. Fourth student 0, 1, 0. And fifth student 1, 0, 0. And now we need to decode it. We can clearly make out that 0, 0, 1 corresponds to AI, 0, 0, 0 corresponds to Java programming, 0, 0, 0 again corresponds to Java programming, 0, 1, 0 corresponds to embedded systems, and 1, 0, 0 corresponds to cloud computing. And that is what we try to look at. Now, can you do, we're saying we know that the cloud computing is taken by most people for Java programming. So maybe we can give shorter code to cloud and longer code to this and see can we save this space. And that is what we'll basically look at. Let's consider one coding scheme for the same case. And let's say we give single bit 0 to cloud computing and 1 to Java programming. And then we can say 0, 0 or 0, 1 to embedded systems, 1, 1 to, so 0, 1 to AI, 1, 1 to embedded systems, and we can say 1, 0 to .NET framework. Now, if you were to do same encoding scheme for AI, Java, let's say 5 students have chosen this subject. First student uses AI, second uses Java, third uses Java, fourth uses embedded, and fifth uses cloud. So what would my encoding would look like? Can you quickly work out and tell me what would the encoding look like for the 5 subjects given the above encoding scheme? Next 1 minute or 2 minute, work out and let's discuss how will work out. You can post it or speak out, type in a chat box. Anyone like to work out and give me the coding scheme? Susmita, would you like to answer? Dhruv Shukla, how would the coding look like for the 5 subjects given that these are my codings? Okay, so one answer given to me is, let's say 0, 1, 1, 1, 1, 1, 0. Same answer is given. So let's look at how do we get that answer. We say AI is 0, 1. So we put 0, 1. Then we have a Java is 1, Java is 1. Then we have a embedded is 1, 1. We put 1, 1. And then we have a cloud, which is 1, 0. And this is what the answer correct is. Perfect. Now let's look at given this. If I were to, somebody gives me this coding, how do I interpret it? I said, this is the coding I got. And given this coding scheme, somebody need to figure out, can this be interpreted as 0 happens to be for cloud? So person at the other end will say, oh, first student use cloud. Second student will say 1, 1. So next is 1 is Java, which second student is using Java. Third student is another, which is again Java. And then we have fourth one, again Java, and we probably end up doing that on 10.net. See, what initially coding was given this, but at the other end, coding happens to be complete and decoding happens to be completely different and erroneous. So that means there is a fundamental flaw in this coding. So unless I separate these codes, like code given was 0, 1, 1, 1, 1, 1, 0. So rather than writing this, we need to put a space or something of that kind. So coding would become 0 for 0, 1 for AI, then we put a space, then we have a Java, which is 1, then we put another space, 1, another space, 1, 1, another space, 1, 0. Now because I am putting a space, this space also takes storage space. So look at what is the total size that happens. I end up taking, though this should take 3 plus 3, 6 plus 1, 7, I actually end up taking 11 spaces. And that is because for separation, I need each separate space, otherwise I could be misreading it. And this is because problem lies in, because when you look at 0, 0 could be cloud computing and 0, 1 could be AI. That means encode of cloud computing is prefix of AI. Similarly, encoding of Java is a prefix of embedded. And that means somebody could misinterpret it. So what we really would like to have a coding scheme. We like to have a coding scheme such that no encoding is prefix of another one. And that is what we like to work out. So let's look at, in this case, this coding we get. And as I said, this could be read as like this, which is not what initially was intended. And hence we have a coding scheme that which is not confusing. If you put a space between separator, that increases my size. Certainly don't want that. And so let's look at how do you go about doing it. And even look at, when I'm doing a normal encoding 3 bits, each one, let's say 0, 0, 0 for AI, 0, 0, 1 for Java, 0, 1, 0, then my average encoding size is 3 bits. If I'm using fixed size, my average encoding is 3 bits. But now with this and a space extra, what is my average encoding size? It is basically, if you look at for cloud computing, the number of bits of encoding of this, if you look at 1 minute, what is that I'm trying to do? 2 into 1 by 4. Yeah. So look at what is happening. Let me explain this. What is my average? When I take all the students, what would be my average encoding size? I know that my Java programming is 25%. That means probability of taking Java is 1 by 4. And Java programming has a size of 1. And plus 1 is separator space, that means it is 2. Look at my cloud computing is a 50% people take it. So probability is 1 by 2. And cloud computing is taken by, encoding is 0. The cloud computing encoding is 0. Plus with separator, I'll take 1 more space. So instead of 3, this should be, 2. Cloud computing takes 2 bits because 1, 0, 1 plus 1 space, 2 into probability of half. Plus my Java is taken by 25%. And Java is encoding a 4, 1 bit size plus 1 separator 2. So 2 into 1 by 4. Plus my, if you look at AI is taken by 12.5%. That means probability is 1 by 8. Now AI encoding is 0, 1, 2 bits plus 1 for separator means 3 bits. So 3 into 1 by 8 for AI, 3 into 1 by, and then if you look at .NET and embedded, each probability is 1 by 16. And again, these are 2 bits, embedded 2 bits, .NET 2 bits, 1 bit per separator. So each takes 3 bit. So total comes to something like this. It may be, I think, 2.25 or whatever that. But can we do better and look at, because this is certainly better than previous where my average was 3, but there's a lot of confusion there. We would like to have better scheme where we want to make sure that no encoding of any subject or anything is a prefix of another one, and that is what we call is prefix-free encoding. So let's look at an encoding scheme, which is 0 is cloud computing, 10 Java programming, 110 is AI, 1110 is embedded, and 1111 is .NET framework. So if you look at no encoding of any subject is a prefix of another one. If it is 0, we know it is precisely cloud computing. If it is 10, it is Java programming. If it is 11, now 11 cannot be there, so I have 110 or 1110. So you take any encoding is independent of, it is not part prefix of any other subject. So this will give me better. So if I were to encode my same subject, can you again work out now using this, what would my encoding be for these 5 subjects? Can you quickly work out and send me the details? Faria, Gagan Suri, Ganesh, give me an answer. I got previous answer from 2, Nikita and Yaswant. I like to answer from other people. Given this encoding scheme, given these 5 subjects, how would this be encoded? Okay, anyone like to give an answer? Kiran, Kavita? Yeah. So I got few answers from Yaswant, Dhruv Shukla. So let's look at what the answers would be. AI encoding is 110. So we get 110. Then we have a Java encoding is 10 for Java. Then we have a embedded encoding is 1110. And then we have a cloud is 0, and this is what the encoding would be. And if we need to decode, we can precisely decode because there's no confusion there. We look at 1101. So we see come here 1, 0, that means not Java programming. So 110, so we know this is AI. 1 encoding is over, start again 1, 0, it is over. That means this is Java. So this is again Java. This is again Java. Then 1110, which is embedded. So this is embedded. And this is 0 is cloud. So using this is called prefix-free encoding because no coding is prefix of any other encoding and hence called prefix. And now look at what is my average bit size for. We know that cloud computing is 50%. So this probability is 1 by 2. And for cloud we have size 1. So it will be 1 into 1 by 2. I'm looking at average size plus my Java programming has 2 bits, means 2 into 1 by 4. Then we have AI, which is 12.5%. AI uses 3 bits, so plus 3 into 1 by 8. and then embedded and .NET both with 6.25%. That means probability is 1 by 16. I'll basically be doing 4 into 1 by 16 plus 4 into 1 by 16, and that is what we'll basically get, and that means my answer would be about 1.875. So previously my average when I do the fixed encoding it was 3 bits, and now got 1.1875, a significant saving of roughly about, I would say, 40%. From 3 bits I've gone to 1.875, so I have a saving of 1.125, which is close to about 335%, something of that kind. Because and this is significant saving, and that is what we are looking at. And now we look at how do we go about doing such an encoding. So primarily, if you look at coding problem is assignment of bit string to alphabets, and code word says you take bit string for each character, do that. So let's take another example. Assuming we have 4 letters A, B, C, and D. A appears 40% time, has a probability of 0.4, B has a probability of 0.3, C has probability of 0.2, and D has probability of 0.1, and total probability has to be 1 because 0.4 plus 0.3 plus 0.2 plus 0.1 is equal to 1. So all total has to be probability 1, and that is what we have to make sure. Now, how can you do encoding? Look, A appears maximum the highest number of times, so we should give lowest encoding. 1 minute. If I were to do fixed encoding using ASCII, since there are 4 letters, I just need 2 bits, and I can give 0, 0, 0, 1, 1, 0, 1, 1, and my average is 2 bits. But if I were to do my optimal encoding, a prefix-free encoding, which I can say A is 0, B is 10, C is 110, D is 111. Look again, each encoding is not a prefix of anything else. 10 is not a prefix of anything. 110 is not a prefix of anything. So this is what we call is prefix-free encoding. Because no code is prefix of any other code. With this case, what is my average size? Look, A appears 40% time and size 1. So it would be 1 into 0.4. B appears 0.3 times, probability of 0.3. Size of B is 2. So 2 into 0.3. Size of C is again 2 digits and appears with probability of 0.2. So 3 into 0.2. And D is again, sorry. I think I made a mistake. Let me do that. If we look at size of A is 1 bit, probability of 0.4, so average is 1 into 0.4. B probability of 0.3, size of B is 2, so 2 into 0.3. Size of C is 3, probability of C is 0.2, so 3 into 0.2, and D is size 3, probability of 0.1, 3 into 0.1, and my average happens to be 1.9 bits. So from 3 bits on the average, sorry, not 3 bits, but 2 bits on the average, from 2 bits on the average, we have come to 1.9 bit. That means about 5% saving. We got some saving. So anytime based on optimal, we do get some saving, and that is what we basically look at. So encoding is basically we do fixed encoding, which doesn't give us any advantage. And in this or other is modes encoding, which is variable length encoding. Some characters who appear more often get more and lower code size, and those characters that appear less number of times a longer code size. And that was the case with modes encoding for telegraph, and they used to have dot and dashes. But modes encoding was not prefix free. It wasn't prefix free, and that means we need a separator, and my size would increase. But we like to have prefix free code, and that basically means no code word is prefix of another, and this makes it optimal efficient. And we'll see how we can take a greedy approach to build the optimal encoding of the, and this is what is called Huffman encoding, so that my average code length, average size becomes less. So let's look at the example there. So primarily Huffman encoding is done by building what we call as Huffman tree. And the way we build a tree, it basically gives us, so build a binary tree. So let's say I have a binary tree. Sorry. So I build a binary tree. And then what I can do is, for the left side, I can give value 0. On the right side, I can give value 1. And that means these leaves, the leaves are basically my symbols. And for these codings, I can basically, so that means for this, let's say A, B, C, D, E. So coding for A would be 0, 0, 0. Coding for B would be 0, 0, 1. So coding for B would be 0, 0, 1. Coding for C would be 0, 1. So coding for C would be 0, 1. Coding for D would be 1, 0. So coding for D would be 1, 0. And coding for E would be 1, 1. But look at, since leaf is not part of path of any other node, each leaf things terminate. So if I were to look at coding only for the leaf using this path, this gives us prefix-free encoding. And that is what primarily what we'll basically do. So Huffman encoding, for example, let's look at the following tree. A, B, C, and D. So code for A is 1. Code for B would be 0, 1, 1. Code for C would be 0, 1, 0. And code for D would be 0, 0. And that is how my code would appear. That basically means I look at only the leaves. So all my character symbols, if they appear in this binary tree, and I assign 0 to the left side, the edge, and 1 to the right side, or I can do vice versa, it will still give me prefix-free encoding, because no leaf is part of the path of any other leaf. So once you assign a code to leaves, it will always be prefix-free encoding, and that is what we look at and see how do you go about building this such a tree or the optimal binary tree. So essentially the way it works is, you initialize, if there are, let's say, n symbols, you initialize all n symbols to be tree by themselves. So each alphabet becomes a tree, and the tree weights as their frequencies of occurrence. Lower the frequency, lower the probability, they have a lower weights. Higher the frequency, they have a higher weights. And repeat the process as follows. Take the two binary tree with the smallest weight, and once you and I'll show with your example. Take the two tree with the smallest weight, join them, and the weight of the joined node is sum of these two weights, and one tree becomes left subtree, other becomes right subtree, and nodes get the weight of both of the subtree together. And that is what we do. And then repeat the process again, including this as a new node. Old node has gone out. When you continue the process, this is the idea of one encoding. So let's take a simple example, then we understand how does it really work. Consider the case, let's say we have 5 letters, A, B, C, D, and E. The respective probabilities are 0.35, 0.1, 0.2, 0.2. So look at sum of all them. 0.35 plus 0.1 is 0.45, plus 0.2 is 0.65, plus 0.2 is 0.85, plus 0.15. So sum of all probability is 1. That have to make sure. And now how do you go about it? So let's say we have 5 nodes, A with a weight of 0.35, B with a node of 0.1, C with a node of 0.2, D with a node of 0.2, and E with a node of 0.15. Now we look at two nodes with the lowest weights. So look at two nodes with the lowest weight. One is B and other is E. So look at the node with lowest weight B and E. So basically make them join these two nodes, combine these two trees into a single tree with the node, so B and E, and join them with a, so at 0.1 plus 0.5, this becomes 0.25, so make a new tree, and so this becomes, so instead of 5 trees now, I have 4 trees, tree with root node A, weight of 0.35, C with a weight of 0.2, do with a weight of 0.2, and new tree, I can call this new tree as, let's say, BE with a weight of 0.25. Now using these 4 trees, I pick up again 2 trees with the lowest weight. So if we look at the 2 trees with the lowest weight is C and D. So I'll combine them, make them another tree, and the weight of the new tree would be 0.4, and that's what we will do. So I left with total 4 trees now, A, C, B, and D, and my lowest tree with lowest weights are now C and D, and that is what we'll combine. And when we combine this, look at what do we really get. So this is a previous case. I combine C and D, and now I'm left with nodes A. So from 5 trees I got 4, and from 4 I got 3 trees. Now which are the trees which have the lowest weights? Would like to answer? Among these 3 trees, which are the 2 trees with the lowest weights? Pavitra, Lata, no. So it is lowest weight is the BE with a weight of 0.25, and not CD, A. Look, weight of A is 0.35, weight of BE is 0.25, weight of CD is zero point 0.4. So 0.4 has a higher weight as compared to others. Weight of A is 0.35, weight of B is 0.25. So my two tree with lowest weight is A and BE. I'll use them to combine, and this is what I will do. So I take BE, I took A, join them, and the weight becomes 0.35 plus 0.256. And now I have another tree which is CD, which comes here with 0.4, and left with only 2. So my two tree with lowest weight is 0.4 and 0.6. Join them together. When I join them together, there's the tree basically I get. Now, how to assign my objective was to assign my encoding. So I'll assign 0 to the left side, and I'll assign 1 to the right side. This is what we'll basically do. So 0 to the left as, 1 to the right as 0, this is 1, then this is 0, and this is 1. So now I traverse the tree from the root and read the labels of the edges, and that becomes my encoding. So if we look at my encoding now, for my encoding of C, my encoding of C is 0, 1, sorry, 0, 0. C gets the encoding of 0, 0. D gets an encoding of 0, 1. A gets an encoding of 1, 0. And then B gets an encoding of 1, 1, 0. And E gets an encoding of 1, 1, 1. And you look at all these encodings are prefix free because I'm assigning codes to the leaves, and no leaf is part of a path of another leaf. Hence, all these encodings are prefix free, and this is my optimal encoding in this case. So if I have only 5 symbols like A, B, C, E, and if I were to use fixed encoding, each would have taken 3 bits. But now in this case, my average encoding bit would be less. If I were to calculate average encoding would be, look at size of C, length of C is 2, probability is 0.2, plus size of C, D is 2 again, with the probability of 2. So 2 into 0.2 plus A, probability is 0.35, and size of A is again 2. So 2 into 0.35 plus B, size of B is 3, probability of B is 0.1. So 3 into 0.1 plus size of E is again 3, probability 0.15, and this would give me whatever the value comes to is average encoding, and this is going to be less than 3, we would basically say. And this is what we'll basically get. So these are my codes, which is what I'll get. And so you look at here in this case, characters with higher probability like A has the highest probability, then we have C and D. So characters with high probability, A, C and D have a shorter code, and characters with lower probability has the longer code. So characters with shorter probability has longer codes, character with higher probability have the shorter code. And that's the reason we look at that. Basically means the nodes which are lower probability would come down at the last level. Node with high frequency, high probability would be closer to the root at a lower depth. And that's the benefit we'll basically get. And that's how my algorithm primarily would come out. So look at the observations. Look at the code tree is a full tree, means each loft tree has exactly 2 children. So look at the previous case. Full tree means a node is either a leaf, or if it is not a leaf, it has exactly 2 children. So each node either has 2 children or it is a leaf by itself. And that's the meaning of what we call as a full tree. You can, to prove contrarily, assume there is a node which has only one child. If it's only one child, I can move that node and compress the tree and maintain the phenomena. So first observation is, if we look at each code tree is a full tree, that means each node has 2 children. Second, a leaf labeled as X is at a smaller depth than a leaf labeled Y, then frequency of fx is going to be greater than equal to frequency of y, or probability of probability of x is greater than, sorry, this should be fy. Let me correct it. So you look at, in this case, the my observation which we are looking at. Let me go back. So first observation was that it's a full tree. Second is Node with at a lower node with a smaller depth has a higher frequency, and node with a higher depth has a lower frequency. And that means, so you can look at from the previous case, you look at this node C and D are at a depth of 2, B and E are at a depth of 3, and frequency of C and D is certainly more than frequency of B and E, and same is true for A. So node with a lower depth has a higher frequency or higher probability than node with lower depth. And that's essentially what we are basically saying. And third observation is, if a leaf at maximum depth labeled as X, its sibling is also a leaf. So again, let's look at this tree here. Node the B and E at the maximum depth. So node B has a corresponding sibling at the same level. So node at the maximum depth would always have a sibling, and that is because, remember, the way we start, we always take two nodes together at the lowest frequency and then join them. So first two nodes which we take would always at the maximum depth because we keep building it up, and that's the reason the observation 3, which is that observation 3 is, if leaf is at maximum depth, then sibling also leaf, and both have same level. So using this, how do we go about building the solution? So look, observation 3 tells us that leaves at maximum depth occurs in pairs, and observation 2 tells us that leaves at the maximum depth must have smallest frequency. So we know that leaves at the maximum the smallest frequency, they occur in pairs. So we can always pick up the nodes with the maximum depth or the smallest frequency and keep building it up, and finally we go to root of the tree, and that's what the solution would basically means. Pick two nodes with the smallest frequency and you start building up by tree, and that is what we have basically done. So we look at the case as Huffman tree, and we've taken the case here, we've taken this case, build up and look at average code length, and then we sort while we've given algorithm as well. So code length or fixed length encoding, when you see in this case, if I do the fixed length encoding, it should take 3 bit, which is 3, but in this case, my encoding becomes 2.25, so about 0.75 saving, meanings my saving is about 25%, with a significant saving when it comes to looking at compression. So a large amount of data, 25% saving, significant amount of saving, and therefore I get compression ratio. And that's the benefit I get. So one is exercise, write this character sequence ACDBA and work out yourself. But let's move ahead. Let's look at my, what my algorithm would basically be. So we already looked at the characters. So let's look at my algorithm. Algorithm is very simple. Start with each node as a tree. Basically, if we look at each node as a tree, so make them the priority queue, which is basically heap. And we primarily build a heap, and we basically build what is called min heap. Either it's a min heap and max heap. Min heap means my root, a node would have a value always less than its children. That means root node would have the node with the lowest value, and so on and so forth. And we know that when you do a heap, my find min takes order one time, whereas delete min, when I delete my min node, it takes order log n time. So essentially what we do, we start with all nodes as tree by itself and make them a heap of size n, and each is basically one node tree, and their weights is equal to whatever their frequencies are or their probabilities are, put them a weight, and now you follow the following process. As long as Q has more than one element, that means since I'm building tree and more than one element, pick first tree with the minimum weight, remove from the queue, which is basically min heap. That means I do a delete min here. So I remove first tree from the priority queue, which is heap. Then I take second node with a minimum weight, again do a delete min. I do a delete min. So now from a tree which was of having n nodes has become n minus 2 nodes. Now I combine T1 and T2 and make them part of a tree. So create a new tree T with T1 and T2 as left and right subtree, and add this tree, and the weight of this tree is weight of T1 plus weight of T2, and add this tree to my queue. So insert into the queue, and this takes my log n time. And that means at this point in time, my tree size is n minus 1. I remove these two nodes, size became n minus 2. I insert one node, size became n minus 1. So in one iteration, if we look at, in this whole one iteration, my size of Q has become from n to n minus 1. I repeat the process, second iteration size became minus 2. Keep doing it till I'm left with only one node. And once you build a one node, you basically got a tree, and then assign the encoding, what will happen. So let's look at the complexity of this algorithm here. I'm running this loop n minus 1 times, sorry, n minus 1 times, because in each iteration, look what I'm doing. I'm doing 2 delete and 1 insert, so tree size becomes always 1 less. That means this loop would run n minus 1 time. Now in each iteration of the loop, I am doing 1 delete min, I am doing second delete min, and I am doing insert. So delete min takes order log n time. This takes order log n time, and this insert again takes order log n time. Remember priority queue studied the heaps. So delete min order log n time, find min order 1 time. So this finding a tree, this is order 1. Finding is again order 1, but since I'm doing a delete is order log n, delete is order log n. Creating a new tree is again order 1 time, because I'm doing 2 tree joining, so this one step operation, but insert again takes me order log n time. And since these operations are done n times, my total time complexity is n into log. And this my total time complexity is for Huffman tree. So using that, that's basically what we do, what is said, my time complexity happens to be n log n. Now question is, where does the greedy approach is? This is greedy approach because we are being greedy. We always take the node with minimum weight every time. So that we are always picking, so my greedy approach, local optimize, take the node with minimum weight, and that's my greedy approach. And this being greedy approach gives me a solution. So now let's do a quick quiz. This quiz is from NPTEL. Given that you have a Huffman tree with 4 letters with their frequency in this order. Now given that frequency in this order, which one of the following statements is true? Can you quickly work out and give me the answer? Given that node has my Huffman tree with 4 nodes, A, B, C, D, with the frequency Fx greater than Fb greater than Fc greater than Fd, Given this, now which of the following is true in this case? Can you quickly work out and give me the answer? Let me know if somebody get the answer. I need to explain why that being the case. You can discuss, tell me. Anyone like to answer? Sujan, Noor, give a thought and tell me what do you think. Only one of them is true. Which one is true? Yes, I would like to an answer out of this A, B, C, D, four statements. Which one is true given this case? And why? Ramya says C. Ramya, can you explain why it is C? I have given the answer at the bottom. If you look at, I have given the answer option C. But explain me why. Can you explain why this answer is C? You need to explain why the answer C is correct answer and A, B, D are not the correct answer. Anyone like to explain? Ramya, would you like to explain? And anybody else? Let's look at the following. Let's draw the case. So we have nodes A, B, C, D, and given to us is FA greater than FB greater than FC greater than FD. That means node C and D with the lowest frequency. So we pick node C and D first. This is my node C. This is my node D. And I join them and this becomes node CD. And I have a node A and I have a node B. Now it is possible that frequency of the weight of CD could be more than that of A, could be more than that of B. Let's consider that the B plus C plus D, the weight of C plus D is greater than B. Or let's look at, we're saying weight of C plus D, FC plus FD is greater than B. And that being the case, and we know that A is greater than B, FA is greater than FB. So that means my B is lowest now. Now whichever is lowest A and C, D, I'll pick. Assuming on this is only given to us for the option B. So let's consider the case where FA is greater than FC plus FD. If FA is greater than this, then what would happen? We will combine B and CD, and this becomes a node which is BCD, and then I have another node. So that means A would have a length of 0, this should be 1, 0, this should be 1, 0, 0. That means node A would have a code of one size 1, B would have size 2, not everything would have a code of size 2. So which is, that means if this is the case, FC plus FD greater than B, that cannot be, every bit cannot be size of 2. Now look at another case. Consider that in the same case, third option, let's look at the third option. Third option is C plus D is greater than A. Given to us is FC plus FD is greater than FA. And we know that FA is greater than FB. That means the CD would have a highest weight. So we need to take A and B, join them together. This becomes AB. And then I'll have a root node for this tree. Now in this case, if you look at, this is 0, 1, 0, 1, 0, 1. Each of the node in the tree has fixed 2-digit code. So, and that's the reason my option C is correct. So if FC plus FD is greater than A, that means CD would have the highest combined weight. So for example could be, let's look at the weights. My, let's say FA, I can say FA is, let's say 0.28, 0.28, FB is 0.26, FC is 0.24, and FD is 0.22. If you build an assignment, each digit, each alphabet would end up getting two bits. But other frequency cases, they'll work out differently. That's what you need to look at. So I'm done for today. So let's summarize what we studied. We basically look at Huffman encoding. We did the Huffman tree, and we basically defined an algorithm. Take the two smallest frequency nodes, make them a tree, join them, and keep building it up. And finally, to assign the codes, all the left edges, label them with 0, all the right edges, label them with 1, and then find the label of all the edges from root to the leaf, and that becomes the encoding of each symbol. That's what we basically did. And the algorithm takes order and log n time, because building a tree, I'm doing 2 delete. 2 delete means 1 insert, each takes order log n time, and since I'm doing n times, it becomes n log n time. If you have any questions, please feel free to ask. Otherwise, tomorrow we'll discuss Dijkstra's shortest distance algorithm, single source shortest path. That will study tomorrow. If no questions, thank you. And by this weekend, I'll also give you third assignment. So I'm working on it. So please look at review. And third assignment will be based on basically greedy algorithm. So review, refresh, and make sure you understand the work on greedy algorithm. If no questions, thank you. I'm done. If you have questions, please feel free to ask.